In this video, we will show how to find the normal force for an object that goes around a loop. For some reason, every time that I think of a loop, I think of Sonic the Hedgehog, that really awesome old Sega Genesis game, and that little loop that he used to go through to correct all those rings. I also wonder why Tails, who I'm trying to draw here, didn't just pick up Sonic and take him across the whole level. Finding the normal force around a loop is a very common Physics 1 example. You will see it in either your homework, your quiz, or one of your exams. It's almost 100% guarantee. To understand the concepts in this problem, it's useful to look at three special situations. When Sonic just begins the loop at the bottom, when he's halfway up, and when he's all the way at the top. Like every other Physics 1 problem, we ask ourselves what type of exercise are we dealing with. We need to find forces, so we're going to have to use sum of forces equals ma. So it's just a force problem. And like every other force problem, it helps to do body diagrams. The other important concept is that the magnitude of the acceleration in circular motion is equal to v squared over r, and that the direction would be towards the center of the circle. This is a good time to remind ourselves that when we do the body diagram, we will not put the mass times acceleration as one of the forces, meaning mv squared over r will not be a force. Alright, let's start with the first situation. Sonic gets to the beginning of the loop. In our body diagram, we remember that the normal force is perpendicular to the track, so it will go up in this case. Gravity will be down. And then we have to think about the acceleration in a circular motion. We know that it will be up since it's towards the center of the circle. So the acceleration will be in the y. It will have a y component equal to v squared over r. And the y component will be positive since it's pointing up. So we write down our sum of forces equals ma equation. Remember that that is an equation for both the x and the y, but here we're only interested in the y since that's where the acceleration is. N minus mg is our sum of forces in the y, and this will be equal to mv squared over r. Remember that n and mg are positive values. They're just the magnitudes of the normal force and the weight. So if I solve for normal force, I get mv squared over r plus mg, both of them positive values. And as we'll see later, this will be the highest normal force magnitude around the loop. The next special situation is when Sonic makes it halfway up. We do another body diagram. The normal force is perpendicular to the track, so it will point to the left. The weight is still down. Another reminder, we don't write down mv squared over r, that is not a force. The acceleration, that's not going in the body diagram. We know that it's towards the center of the circle, so it's going to be in the x, but it will be negative since it's to the left. So the x component of the acceleration will be negative v squared over r. We set up our sum of forces equals ma. We do it in the x since that is where the acceleration is. The normal force will have a negative x component, so we'll get negative n, and this will be equal to the mass times the acceleration negative v squared over r. And the x component of the weight will be 0 since it's pointing straight down. Then we solve for the magnitude of the normal force, and we get that it's equal to mv squared over r. Slightly less than before, since gravity is not in this component. The other special situation is when Sonic is all the way at the top. Same thing, we do our body diagram. The normal force will be pointing down. The weight will also be pointing down. The acceleration is towards the center of the circle, so in this case it will be down. It will have a y component, and this component will be negative. So we do our sum of forces in the y equals the mass times acceleration in the y. Both the normal force and the weight will have negative y components. So negative n, where n is the magnitude of normal force minus mg is equal to negative mv squared over r. We solve for the magnitude of normal force, and we get mv squared over r minus mg. So this will be the lowest magnitude for the normal force in the loop. So now we get to look at the three different situations and write down different speeds for all three of them, since we know that Sonic will lose some kinetic energy when he gets to the top, since he gains some potential energy. The normal force is going to help us get that circular motion acceleration, but at different points in the loop it will either be acting with or against gravity. So at the bottom it has to have the highest magnitude to provide that circular motion. We can get a general expression for any point in the loop if we just write it down as a function of an angle theta. Same thing, we do a body diagram, the normal force always perpendicular to the track, whatever you are, and at any point the weight is always down. In the previous examples, we chose the x or the y depending on where the acceleration was. Here, since it's constantly changing, we're going to do a little coordinate change where perpendicular to the track will be y and tangential to the track will be x. Similar trick to the inclined plane. So we'll write down this weight in terms of its new x and y components. Tangential to the track, it will have a component that will be proportional to sine of the theta. And it will have a component perpendicular to a track that will be proportional to cosine of the theta. So if we do sum of forces equals ma in the y direction, perpendicular to the track, then we will get that n minus mg cosine theta will be equal to m times the acceleration, which is v squared over r. So solve for the magnitude of normal force and you get mg cosine theta plus mv squared over r. And you can see that if you substitute theta for the three situations we were looking at, theta equals 0, then we will get that the normal force will be mg plus mv squared over r. If we look at the second situation, when theta was 90, then we will only have mv squared over r left. And then same thing for at the top of the loop, this should also work. The top of the loop is also useful in telling us when do we not have enough speed to be able to go around the loop. We know that if you don't go fast enough, Sonic will just fall down. So at the top, n was equal to mv squared over r minus mg, and we know that we cannot have a normal force that is negative. We cannot have a normal force that makes you stick to the loop. So the cutoff is when the normal force is 0, and is equal to mv squared over r minus mg. So if you solve this equation, then you can find what is the minimum speed that you have to have at the top so that you don't fall down. And then if you do conservation of energy, you can relate that top speed to the speed when you arrive at the loop.